Yeah, thank you. Okay, let me adjust the screen so that I can see the time as well. So hello, everyone. Thank you all for joining. My name is Atul Kedia. I'm a postdoc at RIT. This work I'm going to be presenting, it's a work that I did in collaboration with my group at Notre Dame, particularly Professor Grant Matthews, Heel Kim at Sogang, and Inseng Su at Oak Ridge. Before going ahead, I want to thank the organizers, including particularly Zach and Leo, for organizing this wonderful meeting. I wish I could be there in person, but unfortunately I couldn't. But anyway, let's go into the talk itself. So my talk title is Neutron Star Merger Gravitational Waves for Quark Matter EOS. In this talk, I'm going to be talking about basically a set of neutron star merger simulations that I do to extract the gravitational waveform for specific types of EOS, in particular Quark Matter EOS. So let me get started by firstly describing just what EOSs are. So EOS it's basically an equation that you need to solve the TOV equation to get the structure of a neutron star. So that it tells you what's the pressure as a function of density, electron fraction, temperature, and so on. So it based on the thermodynamic properties of the neutron or nuclear matter at any position, you can get the features like pressure of exerted by that nuclear matter. So very simply, for binary neutron star merger simulations, you can just think of it as a pressure versus density relation, because in early binary neutron star mergers, the neutron stars are pretty much cold, so the temperature effects can be removed. So this equation of state, I'm showing one plot over here for such an EOS. It's a pressure versus density relation again. As density increases, pressure increases, right? So the EOS is currently very well understood at low densities. So densities below nuclear saturation, 10 to the 14 or so, and even below to the atmospheric pressure can be very well understood right now because of advances in nuclear theory and so on. But at high densities, there's uncertainties, difficulties in nuclear theory, difficulties in observation of things like GW events by LIGO at high frequencies. So those things, I'll get into those in a second, but those basically lead to the fact that the equation of state it's constrained, but not fully constrained. And further, whether there's a phase transition to quark matter is also another thing we are kind of tackling, whether there would be at those really high densities. So whether there's a QGP in a sense, quark-gluon plasma. But there are ways to calculate the QGP phase transition at those densities. What those tend to do generally based on QCD methods, what they tend to do is that they soften the EOS. So what I've drawn here is a sample. It's not one specific EOS, but just an illustration of what would happen. At low densities, the neutron star matter is really just nucleons. At high densities, it's only QGP stuff. But in the region in between, when there's a phase transition, you lose pressure. So while losing pressure, the EOS basically becomes less realistic because even with the GW constraints of LIGO and even more constraints from nicer X-ray observations, we know that the EOS has to be stiffer. It cannot be this soft. Soft meaning it cannot be as like low density. So, but there are ways to. There's recently been proposed a way to tackle this conflict, and it's called QHC, Quark-Hadron Crossover. So what this entails is, at low densities, let's just do the simple hadronic EOS. At high densities, let's do a separate quark matter EOS, like just for quarks. Don't forget the phase transition. And then in the region in between, let's just stitch the two EOSs. So interpolate the EOSs in the region in between where the transition happens. So you don't have that flattening of the EOS essentially. And here's a description. So below 2 times nuclear saturation, it's hadronic. At really high densities, it's quark, and region in between, a smooth fitting is performed. So what do you get? You can have a few different ways of constructing this EOS. So they're labeled, I'm just labeling them as QHC 19, A, B, C, and D. And what I want to do is perform simulations of these EOSs and see whether there could be features of gravitational waveform that can be seen. So to compare that, before going into the simulations itself, let's compare this EOS with a couple of hadronic EOSs Here I'm plotting GNH3 and SLY. So GNH3 is why I've chosen GNH3 and SLY is because SLY is a very it's a very soft EOS, as many of you know, compared to other hadronic EOSs. GNH3 is another hadronic EOS, but it's a stiffer EOS. So that way, if I do simulations, I have comparison of QHC versus soft and stiff EOSs. So given this setup, these are some EOSs that I'm going to show simulations of, Now, how do I perform these simulations? It's using Einstein Toolkit, in particular GR Hydro code in Einstein Toolkit, and I take initial data on Lorine, plug that into Einstein Toolkit, run the simulations, and instead of going into the simulations itself, let's just jump into the results because everyone has seen several simulations here in this workshop. So here are the waveforms on the left-hand side. What you're seeing is QHCs. The top two are QHCs. The next two are SLY, the hadronic EOSs. What you'll notice is they all have merger time being almost the same, about 11, 12 milliseconds. But post-merger is much different. Particularly QHCs have a prolonged post-merger. SLY and GNH3 have a shorter post-merger. But the time frame of the merger of the post-merger phase is not that critical as the waveforms, the frequencies at which these waveforms are oscillating. So that I'm showing on the plot on the right-hand side. So this plot on the right-hand side is a power spectral density versus frequencies.
2 minutes
for these waveforms. So what to notice here is that all these waveforms have peak frequencies at different regions, at different frequencies, frequencies. Like for example, QHCs have a peak frequency around 3.2 kilohertz. So what would be interesting is would be that if interferometers would be able to observe these peak frequencies and tell us that, okay, these are the frequencies to see that we are seeing in the waveform, and so the equation of state would be then just immediate to us that, okay, if these frequencies are showing up, the waveform, the EOS is a QHC versus SLY versus GNH3. But overlaid on top is it's the faint green curve is the sensitivity curve for LIGO, and particularly LIGO sensitivity curve is barely making it to these high frequency.
1 minute, please
features.
conclude.
So so they may not be LIGO may not be able to observe it, but the next gen wave interferometers, ET and Cosmic Explorer that we heard a bit about in the last talk and yesterday as well, they would definitely be able to see these features. Now, going to my conclusion really quickly, or before my conclusion, I want to mention that these frequencies, the pre-merger and post-merger frequencies, can be observed along with some
30
other
seconds.
Can be constrained with some other observable quantities. Particularly on the plot on the left-hand side, you're seeing Fmax, which is a pre-merger frequency plotted against tidal deformability. And the thing to notice is QHC is hanging out along with SLY EOS, and GNH3 has separated out. In the post-merger, which is the plot on the left and on the right-hand side, SLY and GNH3 are both separate, but also QHCs are right in between. They're not hanging out with SLY, and nor are they with GNH3. So now they're behaving a little bit stiffer. So what this means is in pre-merger, they were pre-merger QHC behavior was soft. Post-merger behavior is somewhat in between. It's between stiff and soft. So this is a kind of dual nature, and it's stemming from the fact that the EOS has stiffened up at high densities. And this kind of distinctive features are things that one would be able to see in next-gen gravitational wave interferometers. And so, yeah, with that, I will, and that's the point that we're trying to make. And yeah, with that, I'll leave the summary slide and take questions. And I think I'm running out of time.
Great, thanks, Atul.